Good afternoon. My name is Jean-Louis Briaud. I'm a distinguished professor at Texas A&M University and the holder of the Buchanan Chair in the Zachry Department of Civil and Environmental Engineering. Welcome to the 30th Buchanan Lecture. My goodness. I was thinking the other day, life is short, especially towards the end. 30 years ago, I started this lecture as I had just received the Buchanan Professorship, which came with a spendable account. I wanted to share the good fortune I had and thought of organizing a first-class lecture that would honor Spencer Buchanan and allow everyone in the world to be able to attend the lecture free of charge by funding it through the professorship account and video recording it. I recall calling Ralph Peck as my first choice for the lecture and being surprised that on the phone he said yes without hesitation. The reason was he knew Spencer Buchanan. The Buchanan Lecture went on with a remarkable list of speakers, many of them ASCE-Terzaghi lecturers, or becoming ASCE-Terzaghi lecturers shortly after giving the Buchanan Lecture. It truly has been a pleasure for us to host all those great minds and great people and to honor them as we're doing again today. Now the program. Note that the Buchanan booklet, including the speaker's PowerPoint slides, is already on the Buchanan Lecture website. We didn't make printed copies this year as we're trying to save some trees. We're also video recording this event, and we'll post the video on the Buchanan website within the next few weeks. We'll also give the video to the Geo-Institute of ASCE for them to upload on their website, along with the other 29 lecture videos all the way back to Ralph Peck in 1993. Our first speaker today will be Professor Zachry Graisley, head of the Zachry Department of Civil and Environmental Engineering at Texas A&M University, who will say a few words about our department. Our second speaker will be Professor Greg Baecher with the University of Maryland in College Park, close to Washington. He will deliver his 2021 Terzaghi lecture on the topic of risk. We'll take time for questions. Our third speaker will be Dr. Mark Buchanan, president of the Structural Integrity Group in Conroe and grandson of Professor Spencer Buchanan. He'll give the 2022 Buchanan Lecture also on the topic of risk, but from a very different viewpoint, as you will see. We will also take time for questions. The event will conclude after his lecture, but we'll take a group photo on the stage before anyone leaves. And then after that, there will be a reception at my house that everybody is invited to, 3013 Coronado Drive. If you don't remember the address, let me know. I'll help you out. Now I would like to ask Professor Zach Graisley to come and say a few words about our department. Zach became head of our department recently and has already taken the department by storm. Zach, it's all yours.
Well, howdy, everybody. And for our orange-shirted friends here, it's okay to say that howdy. I think it's being videotaped, but I don't think we're distributing it to your classmates over in Austin, so I think you'd be okay. Taking the department by storm, I mean, with the hurricane and everything in Florida, I don't know that that's the best choice of terms, or maybe you meant it that way, I don't know. So it's my pleasure to be here, and certainly I'm excited to see these kinds of events, particularly this Buchanan Lecture and the Terzaghi Lecture being back in person again after COVID. So I'm certainly happy to see it well attended, and for all of you to be here in this really historic event now at 30 years. And so before I tell you a little bit about the department, which Jean-Louis has asked me to go into very briefly, let's give Jean-Louis a round of applause for putting this together and bringing it back to life again after doing it online and bringing it back in person. I think that it's great, and it does take some effort, especially with all of his other duties. As many of you know, he was ASCE president as well very recently. I think your term ended when did it end? This year. Yeah, just this past year. So it's certainly great to be here. So a few items about our department. I know we've got a lot of A&M students here that are here now that are familiar with our department, and we've got a lot of former students here. But there have been a lot of changes over the years, and Jean-Louis has seen many of those throughout his career, and the department now is perhaps a little different than when some of you might have been there. We are the largest civil and environmental engineering department in the country here at Texas A&M in terms of number of students that we graduate. So sophomores to seniors, we've got between 800 to 1,000 students. Another 400 plus graduate students in the department as well. And of course, we're always growing with all the population growth in the state of Texas and the demand for civil infrastructure. It's certainly a good career to be getting into, as all of you in industry know firsthand. So we're doing our best to produce the next generation of civil engineers, and in particular the geotechnical engineers as well from our department. So some exciting things going on within the department. I can't take credit for these. I mean, the great thing about being a department head in a department with a storied history of ours and the great group of former students that we have is I can kind of sort of sit there and take credit and benefit from all the hard work of other people. But if you've not seen our Center for Infrastructure Renewal, that's been a great addition over the past few years. It's out on the Rellis campus where the test site is that Jean-Louis put together for many years out there. Now we have a fantastic lab. It's a $80+ million lab. I think it was 80 million when we built it. I say 80 plus now because that was in like 2018 dollars, which is, I don't know, 40 million now maybe. I'm not sure how the inflation's working today, but anyways, that's about 135,000 square foot facility to do all kinds of R&D for civil infrastructure. And so if you've not seen it, make it a point. Dr. Anand Papala where's Anand? In the very back, hiding back there. He's the director for the CIR, and so he will make sure to give you a tour, or find somebody who can do it if he's not around. So reach out to him if you'd like to see that great facility. Some other exciting things, we've had a lot of retirements in the past year, which, I ask people, is that because I became department head? And, they assure me it's not. But in any event, that's certainly it's got its downsides, but it also presents some opportunities as well. So we look forward to hiring some additional talented young faculty over the next few years, and really look forward towards expanding our impact and the types of research we do, looking towards new technologies like the inclusion of data sciences into civil and environmental engineering, sustainability, reliability and resilience. And I know we're doing these things already, but really formalizing them and emphasizing and expanding on that while retaining our strengths in some of the core traditional areas that are still important within civil engineering. So I think it's a great time to be a civil engineer. I think it's a great time to be at Texas A&M, and it's certainly a great time to be bringing this lecture back online and in person. And I really look forward to hearing the seminars today. So thank you all for coming. And Jean-Louis, I'll turn it back over to you.
Thank you, Dr. Grizzly. Your support is very much appreciated. Before I introduce Dr. Baecher, I want to thank you for attending this lecture over the years, and in particular the students from the University of Texas at Austin. You've been solid in your attendance, and we very much appreciate that. And always enjoy having you at the house afterwards. Now it's my great pleasure to introduce Professor Greg Baecher. Note that Greg gave the Buchanan Lecture in 2019 and was chosen as the 2021 Terzaghi Lecturer 2 years later. Before I read of his accomplishment, I sometimes think of people as smart and nice, smart and not nice, not smart and nice, and not smart and not nice. Dr. Baecher is definitely smart and nice, and very unassuming at that. Greg, it's a real pleasure to know you. I'm not finished with the introduction. Hold on a second. Dr. Baecher is the Glenn Martin Institute Professor of Engineering at the University of Maryland. He holds a bachelor's degree from UC Berkeley and a Ph.D. in geotechnical engineering from MIT. He's the author of 6 books on risk, safety, and the protection of civil infrastructure, and over 200 technical publications. He's the recipient of the U.S. Army Corps of Engineers Commander's Award for Public Service, the Panamanian National Award for Science and Technology Innovation, the Geotechnical Safety Network Distinguished Achievement Award for Contribution to Geotechnical Reliability, and is a member of the U.S. National Academy of Engineering and the University of California, Berkeley Academy of Distinguished Alumni. It is my pleasure to invite Dr. Greg Baecher to deliver his 2021 Terzaghi Lecture entitled Geotechnical Systems, Uncertainty, and Risk.
Thank you so much. So, Jean-Louis, thank you so much for that too long introduction, but very kind. And I would just, in response, I'd like to say that Jean-Louis has done such a fabulous job, especially these last couple of years, by being president of ASCE and now hosting these lectures for 30 years. Time goes by, but he's just done a fabulous job, and I think we should give him another round of applause, if quickly. Well, I am just pleased to be here. I was here, as Jean-Louis said, sort of bookending I don't know if this is a good thing or a bad thing, bookending the pandemic. So I was here in 2019, for the 27th Buchanan Lecture, and here I am again. At that time, Jean-Louis said, often people who give the Buchanan Lecture do the Terzaghi Lecture a couple years later, and I just wonder if he had his thumb on the scale about getting me chosen to do this a couple years later. I'm an academic. I've spent my career working in this area of uncertainty, probabilistic modeling, geotechnical risk. Mark and I are probably going to talk about very different ends of the risk spectrum, and that's good. I'm looking forward to hearing that too. I'm going to talk about something that has occupied a lot of my time these last decades, which is large geotechnical systems and appraisal of the engineering, not the business, the engineering risks that we face on some of those projects. As Tom O'Rourke said some years ago when he was doing his Terzaghi Lecture, nobody works alone. Everyone builds on the shoulders of other people, and I won't go through that's a very short list of the many, many people that I would need to acknowledge about the comments I'm going to make in the next hour. But suffice it to say that there are many people to whom I owe a debt. Almost nobody more maybe than John Christian, who some of you know. He was my favorite professor at MIT, my great mentor throughout my career. He and I wrote a book years ago, and I'm just so sorry to say that John passed away in June. And so I would like to, I'd like to think he would have liked this lecture, and I'd like to dedicate the comments I'm about to make to his memory. If you go back and look at the Terzaghi lectures over time, there have been, depending how you count, 3 and maybe a dozen that focused on the issue of uncertainty and risk, well, certainly on uncertainty. The first of those was Arthur Casagrande in the second Terzaghi lecture. Ralph Peck was the first in 1965. And that was a famous paper which I presume and I hope that all of you have read at least a few times, which was called The Calculated Risk in Earthwork. Casagrande didn't actually do any calculations in that paper. It wasn't really a quantitative risk calculation, but it was a seminal paper and informed a lot of subsequent geotechnical practice. 20 years later, Bob Whitman, who I was also very honored to study with at MIT, did his Terzaghi lecture in '81, published in '84, in which he attempted to put numbers on Casagrande's lecture some 20 years later. And he talked about a quantitative approach to calculating risks on large projects. And I'm going to reprise a project that he talked about in his lecture some 40 years ago, which I think still today, so many years later, holds a lot of lessons for us. And then 20 years after that, John Christian gave his Terzaghi lecture also on the same topic, and in which he updated what Bob had said some years before. So where are we going? Well, first of all, why do we care about appraising or calculating or analyzing engineering risks on these large projects? I'll answer that question in just a second. We're going to talk about what we've learned about doing that process. What have we learned about the undertaking, the engineering undertaking of trying to understand the uncertainty and risk on large projects, which I'll talk about in a minute. And secondly, a lesson that has come to us while trying to do this is exactly how should we think about uncertainty in geotech? And there's a lot of different ways of doing that, and I have a reasonably strong opinion on this topic, and I will try to share that with you. So I'm going to talk about 3 projects. I took out the Tampa Bay because the lecture was just too long, so I apologize. If anyone wants to talk about Tampa Bay, we can talk about it some other time. But I'm going to talk about the Tonin project, which was the sort of the backbone centerline topic of Bob's lecture so many years ago. And why did people care about risk on that project? Well, the problem was Tonin was and is a large tank farm in Kawasaki in Tokyo Bay. And this is the late 1970s, early 80s. And the worry was that being in a seismic area, being on hydraulic landfill, that the liquefaction might get triggered and there might be large deformations. The tanks might lose oil, lose storage. There were very many complicated systems of revetments and firewalls and drains, but all of those systems might get compromised and they might lose oil into the bay. And their appraisal at the time in $1980 was that was going to be about $1 billion cleanup, so whatever that is. I don't know what that is today given inflation, whatever that is today. And the president of Tonin at the time had been a graduate of where else? Harvard Business School. And when Bill Lamb, who we were all working for at the time, went and started to talk about factors of safety, he said, wait, stop it. Don't tell me this mumbo-jumbo factors of safety. Tell me probabilities of failure that I can deal with. And so we set about to do a risk analysis. The second project I'm going to talk about is the IPET, the Interagency Performance Evaluation Task Force following Katrina, stood up by the Corps of Engineers with a task force of, I don't know, many hundred engineers and scientists. And the problem there was, well, how safe was the hurricane protection system? The Corps of Engineers doesn't call it that. But how safe was the protection system surrounding New Orleans before the hurricane? How safe was it going to be after the hurricane? And what was the risk to the exposed population, the risk to life, not the risk of money, but the risk to life of the reconstructed hurricane protection system? So that was why they wanted to know. There's lots of funny stories about that. Maybe some of them I'll get into. And the third one is very recently, the Panama Canal operations and chronic risk study. And the problem there was the canal is a huge, complicated system of engineered works, of capital investments. It faces a number of natural hazards that were unknown at the time of construction, but are now known and others suspected. And the issue was how are the risks mitigated by operational decisions that the management of the canal can make. And so that was why the Panama Canal Authority was so interested in understanding risks. So let's talk first about Tonin. So this is a recent picture of Tonin. Those three areas in green are large tank farm areas. Just to put things in perspective, you see these, I said, Jean-Louis, I wasn't going to use this, but I am. You see these tanks there? Those are 50,000 kiloliters. I did a calculation the last time I gave this lecture. I think that's something on the order of 18 acre-feet. Maybe it's 20 acre-feet. It's a lot. These are big. These things are divided into patios, which are separated by firewalls. There's a huge firewall revetment around the whole outside. There's a whole bunch of drainage. And the issue is, how susceptible was this site to liquefaction? What was the probability that a loss of product off-site into the bay might happen? And what should the management of Tonin do about it? And that is, how much money should they be willing to invest in reducing this risk? Because the risk was large. I'll show you how large in a minute. Well, Bob Whitten was the technical lead on this, and Alan Marr was involved, and Mishak Yagi and me and a few other people. And so we set about to we set about to try to understand the problem facing the Tonin management. And down the hall from us at MIT in those days was Norm Rasmussen. If that name may mean something to a few of you. He was the project director of the WASH 1400 study. Remember that? That was the nuclear reactor safety study that US NRC contracted in the mid to late 1970s. And they were using all these new risk tools. And so we, in the nature of academics, we decided, well, we could borrow some of those. That's a fancy word for steal. We could borrow some of those tools. And so one of them that we borrowed was the idea of event trees. This is all ancient history. We use event trees. The dam safety community here in the States uses event trees for everything, right? But in those days, this was kind of something that people weren't doing. And Bob thought we should really do it because he noted that, this system of facilities could fail in a whole bunch of different ways. And we can't just go calculate the reliabilities of some footings or some tanks or something. We have to consider the system as a whole to understand the risks. And so we decided, so I was over with Zenon this morning talking to his fabulous graduate students, and they have their own version of this picture, which I think of as the TVC picture, the threat, vulnerability, and consequence. This is now the standard way to do a lot of big systems risk analyses. It's been criticized in certain areas, but usually not in engineering. And so we adopted this where the threat was the earthquake and the liquefaction, the vulnerability was the fragility of the tanks and the walls and all that, and then the consequences in this case were mostly fines, actually, mostly environmental fines if Tonin released product. So that got us off on a sort of a reasonably solid footing of organizing the uncertainties. That's sort of a theme here. The second thing we bumped into, and I think we learned some lessons, was the geotechnical data were really difficult to deal with. This is late 1970s. The only data we had were SPT blow counts, by which, given Harry Seed's work, Bob and others were attempting, and Mishak were attempting to correlate those to liquefaction triggering. But whoops, I'm sorry. But look at these data over here. This is the upper fill. This is a hydraulic sandy fill, and this is the in situ native alluvium. This alluvium is not too bad. This sandy hydraulic fill was the bad actor. But look at the coefficient of variation, right? The standard deviation divided by the mean. It's about 50%. If you put those numbers in any probability calculation, you will find out that the site failed a long time ago, right? It's no longer actually standing there. So that couldn't be real, or at least it wasn't very usable. So we thought we needed some way of explaining the data, And we came up with this little cartoon, which has been used a lot. You see it around a lot these days, but this is where it originally came from. And this divides out the uncertainty in those data into two pieces, into the data scatter that you actually observe, which was really large, right? And into systematic errors, which are much more dangerous, that you don't observe. So that is measurement bias, right? That is statistical error in the mean or in the spatial trend. Over on the data scatter side, some of that data was real. I mean, it actually, there's nothing random about soil properties. They are what they are, and they are variable. But also some of that scatter, we thought, was coming from just measurement noise. And it took a while. It took the work of Don DeGroot now at UMass some years later to kind of come up with good methods of separating those two, the noise from the trend in the geotechnical data. But I think today we have a good handle on how to do that. So that was the second thing. The second hurdle that was explaining the data. There was a bunch of other things we learned too, but these I think were the three that have stuck with us. And this cartoon, maybe some of you have seen before. I know Jean-Louis has seen it because we have had many, many talks about it. And this diagram has evolved over the years. They're much more elegantly drawn, drafted today, but the concept is the same, right? Along the x-axis is cost, consequence of a failure. Along the y-axis is a probability. Now Alan Marr and I put this figure together over a long weekend with a few glasses of wine. Probably not as good as what Jean-Louis serves, but they were refreshing anyway. And we weren't quite sure in those days whether we were talking about, for those of you who are in this world, big M, big F, little n curves, or little f n curves. That is, annual exceedance probabilities or annual probabilities. So this is regretfully a mix of both. Today we probably wouldn't do it that. And then we took a big heavy HB pencil and we drew those lines of two kinds of risk, things which people seem to accept readily and things which sometimes they accepted if the benefits of the risks were large. And we went to the owner and we said to the Tonin management, and we said, your annual risk is X. The annual risk was a lot. The annual probability of a serious failure, as you said, the blue is where we thought the site sat. And so that was about a 1 in 100 probability of a significant failure. And if you multiply just back of the envelope, 1 in 100 times a billion, you get a big number. And so we went to him and said, you ought to be thinking about that kind of investment every year, or at least at one time, to reduce these risks. And they said, geez, I don't know, we're not sure we want to go there. So we came up with this plot. The purpose of this plot was not to say prescriptively where they should be in risk, but to say descriptively where do they sit compared to other people. So that was the purpose. The purpose of this was risk communication, and for that reason, to that end, it worked really well, because we went and we showed the management of Tonin this blue dot, and we said, we thought that maybe if you could get your risk down by about an order of magnitude, down to where those lines are, you could go to the regulators and you could tell them in good faith that your risks were consistent with international good practice on large engineering projects. And surprising to us, that's what they did. And it worked. They did end up remediating the site eventually, about 10 years later, but yeah. So that was the purpose of this chart, and you will see this chart. It's usually called the Whitman chart, because Whitman, Bob, put it in his Terzaghi lecture. And this is one of those, Alan Marr and I always talk about, this is one of those, if you don't know it, this is one of those manifestations of Stigler's law of eponymy. Do you know this? Stigler is a famous historian of statistics at Chicago. Stigler's law of eponymy says that every great mathematical equation that's named after somebody is named after the wrong person. So that's Stigler's law of eponymy. Anyway, so these are some lessons we learned. We learned some other lessons about spatial averaging and stuff too. Okay, a philosophical digression. There's nothing uncertain about geotechnical engineering. It's just that we don't know enough. No, there's nothing random about soil properties. They are what they are. We just don't know what they are, typically, or we only know what they are at a few points. And this is a famous saying from Georges Maturon. You probably know Maturon, the famous professor at the Paris School of Mines who invented geostatistics. Probability is in the model, right? It's our conception of uncertainty. That's the probability. Probability is not in the ground. Geology is not uncertain. Unless you're a high-energy physicist, in which case maybe it is, but for us it's not. The second thing we learned, uncertainty is in the mind, right? Uncertainty is not in the world. This is controversial. I'm going to make a pitch in about 5 or 6 slides that we should be thinking about uncertainty in geotechnical engineering in the sense that Bayes or Laplace thought about uncertainty. Uncertainty is epistemic, it's in the mind, it is not in reality. Reality is deterministic. Now, high-energy physicists don't believe that, but I believe that, right? I believe that if we really knew all the atmospheric conditions, if we knew all the boundary conditions and initial conditions, we'd be able to predict stream flow without historically going back and just doing statistical analysis, right? That's the Laplacian determinism argument. I think it's totally true of geotech, is that our uncertainties, they're in the model, and they are not frequencies, they are in the mind. They're epistemic uncertainties. All right, enough for the digression. Hurricane Katrina, this is interesting. This is 2005 through about 2010. A number of the people, some of those people are known at least to some of the people here in the audience. Ed Link was the head of the IPET, and we all remember Louisiana. The issue here, the thing that the chief of engineers, the question he presented to the working group on this project was, did the whole hurricane protection system, now called HISDRIS, which I can never remember what that stands for, did the whole thing work as a system? Well, spoiler alert, no, it didn't work as a system. It hadn't even been entirely completed in 2005. There are big areas where the system had never been built. But how do you go about appraising the risk on a big system like this? It's 350 miles of levee. We walked and drove every single mile of them. And on the right-hand side, you can see the engineering model that we tried to build to represent the 350 miles. In today's jargon, the digital twin of the truth on the ground. And we divided up the whole system into 165 reaches that we thought were more or less homogeneous in soils and load and consequence. The blue points there are individual crossings of the levee system by pipes or gates or other things that we all modeled using structural reliability. And we tried to put all these things together into one large integrated system to try to understand the probabilities that if certain storm characteristics came ashore, that you might get breaches and so forth. And we learned some things from Tonin, which had been 15 years earlier. By now, we came up with a nicer, at least better drafted model of the TVC, the threat, vulnerability, and consequence. This one is due to Marty McCann. It turned out that at the same time that we were doing this, Marty was on our team, and Marty was also on the California Department of Water Resources team doing the California Delta Levee risk study. So he very kindly allowed us to steal their TVC model, which we used, and it was an upgrade of what we had used in Tonin. It seems to work very well. We continue to use this overall breakout of threat over on the left-hand side, the systems model and vulnerability in the middles, and consequence on the right. Spoiler alert, a really painful lesson is that event trees seem like a great idea, but they don't scale at all well. We ended up, the team that was doing the event trees ended up with event trees with between 3 and 4 million end nodes being done in Excel. I don't hear any of the students who are Python experts laughing, but you should be, because this was a disaster. By the time we learned that it was a disaster, it was too late, and so we had to continue on. Today, I think surely we would do this with simulation rather than doing it with event trees. So the TVC approach seems to work. It continues to work. And like I said, even this morning I was looking at the research you guys are doing here, and you're using it pervasively through a lot of stuff. Another thing we learned on Tonin was that you can't redo everything. We can't reinvent the wheel. We couldn't go back and do exploration and slope stability and hydraulic analysis for 350 miles of levee. There wasn't time, there weren't people, there wasn't money. So we had to rely on the legacy, the archival analyses. And not surprising, do we have anyone from the Corps of Engineers here today, maybe? Too bad, I was going to say, good for you guys. I mean, the Corps in New Orleans, they had every drawing they'd ever made on the levee system. I mean, going back to who knows when in colonial times. And they had every boring that they had ever taken all recorded and all electronically digital in databases. So we were able to build on the legacy analysis. It wasn't perfect, but it was, it was what we had. And then one last thing that I think really came home clear on this was risk people talk about, I've already mentioned it, talk about aleatory uncertainties, randomness in the world, right? So we often treat stream flows as random and inherently random. And whether they actually are or not doesn't matter. We can model them that way. It's sort of like modeling them as if you were modeling flips of coins. There's another kind of uncertainty which is dominant in geotech, which is we don't know enough, epistemic uncertainty, what we know. We used to, certainly when we did Tonin, we just mixed those two together. I mean, we tried to be careful, but we mostly just mixed them together. Shouldn't do that. That's something we've really learned. You need to separate out the epistemic uncertainties, like model uncertainty, parameter uncertainty, all those engineering uncertainties. You need to separate those out and analyze them differently from things you're assuming to be spatially or temporally random. And we've learned ways to do that. On the left-hand side, something we don't use a lot anymore is the so-called approach of probabilistic seismic hazard analysis, which is event trees where you take all the epistemic uncertainties and put them into a logic tree on the left-hand side, and then you condition everything else on that realization. I think today we're doing more of the stuff on the right-hand side, as is the core, where we do simulations, but we do nested simulations where we do the aleatory simulation, and then around that we nest the epistemic uncertainties. And that seems to work exceptionally well, and it's a heck of a lot more efficient than the left-hand side. Okay, one more picture. This is where we have come from in FN charts. This is a modern FN chart from. This is from the IPET report, but it mimics the Corps of Engineers, the Bureau of Reclamation, FERC's, ANCOLD's, all the dam safety people use this way of representing risk. The blue dotted line is ANCOLD, that's the Australian New Zealand Committee on Large Dams, criterion for existing dams. That is number of fatalities. This is no longer dollars, it's fatalities versus annual exceedance probability. The colored lines, the red is what Marty and his crew from I might just blank, in the California case, calculated for the California Delta levees. So that the numbers of fatalities drops off quickly because the population at risk is limited to not many people. The orange curve is what we calculated as the existing risk in New Orleans prior to Katrina. The bluish purple is the updated post-reconstruction numbers. And you can see, so more dangerous is to the upper right? More people killed, higher probability. More safe is to the lower left. You can see those numbers are 2 to 3 orders of magnitude higher than what the dam safety community thinks are prescriptive, where you should be. I love this quote. It's from Henry Petrosky. Safe is not an engineering term, right? Risk is an engineering term. Probability is consequence, cost. Those are all engineering curves. Safety is a political term, right? It's a political and social term. Why is that purple line way up there near a 100-year return period? It's because by act of Congress, that was the safety level, okay? It has nothing to do with what engineers decide, and engineers shouldn't be deciding, okay? Anyway, that idea of FN curves has also evolved a lot over these decades. Another digression. I used this term when I was here in 2019, and we got a big laugh in the audience. I don't hear anyone laughing today, but it's still true, right? The statistics you all learned in college is totally useless in geotechnical engineering. Why is that? First of all, the statistics you learn is all based on frequency. It's based on clinical trials. It's the statistics of political polls. It's the statistics of the national census. It's not the statistics that engineers use in trying to make decisions, and I'll tell you why in a minute. Secondly, it answers the wrong questions. And here's the way we should be thinking. This is Bayes' theorem. And Zenon, where are you? Zenon showed me that you have Bayes' theorem embedded in your pavement out near the there you go, out near the engineering school. Bayes' theorem is how engineers think, and it's the observational method. Bayes' theorem is the observational method. It's how we should be thinking about uncertainties in geotech. And what this says over here, there's some probability that you have. It's probably, if you believe me, it's a degree of plausibility or a degree of belief, a degree of confirmation. It's not a frequency of like flipping a coin. It's the probability that we assign to something being true. Is the model approximately correct? Are the soil properties approximately this? Is there a sinkhole at this site, right? And we go out and we collect some evidence. In statistical jargon, we call that the likelihood. It's the probability of seeing the data you actually saw if that hypothesis, if that thing were actually true, right? That's the weight of evidence. All the weight of evidence is in that one term. When you multiply those two things together, you get an updated probability. So that you can see why this is how the observational approach works. We have an original appraisal of probabilities, we monitor the project, we get some new data, and then we update our uncertainties. And that denominator, you can forget it, it's just a normalizing constant. Most people today just numerically get rid of it, it's not important. The take-home lesson is the observational method is not limited to the observational method. It's not limited to performance monitoring. It applies to everything that we do in geotech. And this is the reason, and then I will move on, given the hour. The probability you learned in college is direct probability. It goes from a hypothesis, the state of nature is such and such. We don't know it, but we're just going to hypothesize that it is. Presuming that's true, what's the chance that we would have seen the data we actually saw? Well, in fact, what's the chance that we might have seen data other than we saw? That goes into traditional statistical calculations of confidence limits and p-values and all that sort of stuff. That's direct probability, sampling probability. That is not actually, this sounds subtle, maybe it sounds meaningless, but it's not. It's really important mathematically and logically. What we are doing is we see the data. The data are not random. We don't care what the probability of the data is. The probability of the data is 1. We saw them, right? We know those are the data. The question is, what's the inverse probability? If we've seen those data, what's the probability on the state of nature, on the hypothesis? So direct probability goes from hypothesis to data, which is not what we want to do. Inverse probability goes from data to hypothesis. Today, we normally, for shorthand purposes, we normally call that the Bayesian way of thinking about uncertainty and probability. And I would maintain to you that H&H engineers, hydrologists and hydraulics people, are all frequentists. They think of the frequency of stream flows, the frequency of rain. Geotech engineers, I think almost to a person, are all Bayesians. We may not know it, but we are. We all think about going from data to what's the chance of the state of nature being something, right? And I would say for all of you structural engineers, most of my structural engineering friends don't really care. They only care if we're meeting code, right? So, I'm sorry. You structural engineers can tell me off later if you want. Okay, last quick example, and then I'll wrap up. So this is a project we just finished, the Panama Canal Authority, the operational and chronic risk study. And this is, for those of you who are not real, the Panama Canal is just such a fabulous place and such an interesting, knowledgeable group of engineers working on it. This is Gatun Dam. little travel log. This, when it was built, was the largest dam in the world. Jean-Louis, the ASCE leadership said this dam could not be built and should not be attempted. But Theodore Roosevelt said, heck with the ASCE, and ordered the Corps of Engineers to build it, and they did. The downside of this dam is its hydraulic fill. And in the turn of the last century, in 1900, 1910, everyone thought that there were no earthquakes in Panama. Well, it turned out not to be true. It turns out there's actually a significant earthquake risk in Panama, and this dam is now, this is a dam that is getting a lot of attention because it's very loosely filled. But there's a whole bunch of other things at Panama. That's the canal. You've probably seen pictures like this. There are 3 major dams in the canal zone. There are about 20 or so saddle dikes, which basically are dams, because if any one of those goes, Lake Gatun goes. And if Lake Gatun goes, the canal goes down, and it takes 2 years to rebuild and 2 or 3 years to refill it. And so you're talking 8% of the world's maritime commerce, which would be shut down. So consequences here are potentially large. There's a waterwork plant. There's an electricity plant for the city of Panama. There's all sorts of stuff going on here. And the issue is, what should the operations and the engineering teams at the Canal Authority be doing to mitigate these risks, to minimize them? This was a little bit different. This system is huge, right? It's huge and much more complicated than those other 2 systems. So one of the first things we did, which I think certainly in DC, all the federal agencies do this as soon as they're starting a big project, whether it's in construction or anything else, is they put together a risk register, right? A list of all checklist, right? All the things that might go wrong in the project. This is just in Excel. Typically this list 50 or 60 items. In this case, it was 600, but we narrowed it down to a few. This turns out to be an enormously useful thing. The dam safety people call this semi-quantitative risk analysis. It's just a checklist. So the organizing power of simple checklists and qualitative thinking, I think, can't be overemphasized. This is the famous East Calibra Cucaracha slide. This is one that Arthur Casagrande himself was the principal consultant on, a principal consultant. We ended up having to use a lot of legacy analysis in this project. That's something that we've seen in a lot of these big projects, so you can't redo everything. And we ended up here with, again, plots that looked like this. These are the risks associated with the Calibra cut slides. This has been a classic case of soil mechanics since the beginning of soil mechanics, right? It's like Casagrande was one of the big people working on it. The Waterways Experiment Station worked on these slides for years. They blacked out. Well, this is cost. This must be the slide that you said didn't come through. Anyway, it didn't go through. Cost along the x-axis, annual probability of exceedance along the y. Those are the same 2 lines from the Whitman chart. Look at those black points. Those are slides, empirical slides that have historically occurred. Way above. I mean, but what can you do? That's the cost of doing business. So they just repair them, right? It's not even a risk, because you know they're going to happen, and they seem to happen at this very constant frequency. The red ones are things that Matt Dupuis, who was the head geotech down there, retired now, calculated. Those are seismically induced slides. They are, even though everyone is really frightened of them, they're actually, from a consequence probability point of view, a lot less important. But communicating risk in this way really had a huge impact. Let me just show you one more slide, and then I'll wrap up. This is a slide that Luis Alfaro, who was now retired, was the vice president of engineering for many, many years at the ACP. And this is a slide. This is how Bob Pativ and I got involved, helping them with the chronic risk study. Is that shortly after Whitman's Terzaghi lecture, Luis was the alumni of the year at Purdue a few years ago. Very competent, well-known engineer. Luis came up with this way of going to the board of directors. Now, who's the board of directors? Mark, I don't know, your board of directors probably has a bunch of engineers, but the canal is mostly lawyers and accountants and politicians, right, and the wives thereof. So he went to the board with this plot, right? He redrew this. This is cost along the x-axis, annual probability along the y-axis. Those are the two lines from the Whitman chart. And he said, look, that blue circle is where we are today in Culebra, right? There's a high, you can see from the historical data I just showed you, right? That's those black lines, right? That's where we are today, sort of qualitatively. And if we install this real-time, continuous, 24/7 monitoring system, capture all the data on computers, show it in our Star Wars geotech lab, we can probably lower our probabilities by about an order of magnitude. And on the basis of a communication picture as simple as this, he managed to convince the board of directors of the canal to invest several tens of millions of dollars in installing real-time monitoring, which continues to this day. And you can go into the geotechnical offices at the Canal Authority, at the engineering division, and they have all of these data, real-time, showing you the deformations and pore pressures and other things in the Culebra Cut. Okay, so let me wrap up. Well, we've spent a few decades trying to appraise quantitatively the engineering risks on these large systems. And these large systems are engineering systems involving a large number of components which are all interacting. Failures can occur in a wide variety of different ways through combinations and permutations which are often hard to predict a priori. But management, from the engineering point of view, often wants to have a sense of the size of these risks so that they can make reasonable financial and engineering decisions to reduce expected cost, to price out risk transfer. I haven't mentioned that, but that turns out to be a huge piece of all of this kind of calculation. How much should we be paying to transfer risks to someone like a reinsurance company, right? I mean, this is not auto insurance where I go to Geico and they tell me it's going to be, $300, take it or leave it. I mean, if you go to if you're the Panama Canal, there's room for negotiation on what you're going to pay for insurance. So how much should you be willing to pay? Should you go to the financial markets, and should you float catastrophe bonds and other ways to transfer the risk to other people? And if you do, how much are you willing to pay for it? So there's a lot of reasons for doing this. So what have we learned over the years? Well, I mean, we've learned, I think, that the risk analysis approach that I've described, and lots of people practice this way of thinking today, it's still evolving, but it's becoming pretty mature. I mean, we have relatively good ways of doing this stuff today. And it seems to have been successful in a number of very large projects. And I mean, certainly in the offshore area, this is also true, right? Some of the things that we have learned about methodology, about probability models and statistics. I cannot emphasize how much what you learned in college you should probably forget, unless you're worried about clinical trials. But if you're worried about probability and risk in geotech, we need to be thinking of this in a more Bayesian kind of way, right? Using inverse probability. And I skipped over one of those slides. A lot of the early work in this way of thinking actually came out of geology and geophysics, not just out of statisticians. Something I could not illustrate today, but I know several of the students here are probably well aware of it, is that this way of thinking, from a methodological point of view, mathematical point of view, actually allows you to make much stronger conclusions and inferences with much sparser data sets than does traditional statistics. And it is the foundation of what all civil engineers, not all civil, all geotechnical engineers pride themselves on, which is the observational method. Well, I hope that this was useful, and I thank you for all of your attention. And JL, I don't know if you want to take questions or just leave them for, okay. It was either so overwhelmingly confusing and poorly stated, or so obvious.
I have one.
Okay, great.
On the Panama Canal, the blue circle dropped down to the red circle through monitoring. I don't understand. How can
because
you decrease the... To me, if you monitor, that means you can see the failure coming and you can move the ships out, so you minimize the consequence.
but in Calibra, you can also intervene in the geology. You can
Drain?
Usually it's either backfilling or cutting. So you can come in, backfill the toe,
Ahead of time.
cut the crest ahead of time. Well, I mean, the deformations are slow. It's not like you go out one day and tomorrow it fails. I mean, it's moving for maybe months.
Yeah, yeah. Okay. I got another one.
Great.
We, at the national site, we've run some very large-scale footing tests. We first did a cone penetrometer test at one location and a cone penetrometer test at another location. They were very different. And we said, all right, well then the footing tests are going to be very different. And they were not. So that led us to believe that scatter or heterogeneity is scale dependent. That at the scale of the cone penetrometer, you can detect large variations, but at the scale of a footing where you have an integration of the variation. So how, if we get the coefficient of variation, for example, from cone penetrometer, how do you take the scale into consideration?
Boy, I could talk about that one for a long time. Thank you for asking it. One of the things I dropped out of this lecture that was in the original Terzaghi lecture was the issue of spatial variability and scale. Okay. And the proportional variation of soil properties is a function of the volume of soil that you're concerned with, right?
Absolutely.
Yeah, and so and this was something that Maturone pointed out about mineral deposits in the 1950s, is if you look at a specimen the size, a zone of soil the size influenced by a standard penetration test in these data, the variability among those small volumes is very, very large. But if you average under one of those 62-meter diameter tanks, the variability among the averages of the different tanks is very, very much smaller. And one of the things one sees, and this is a warning, you see these people doing geotechnical reliability calculations, and they're calculating probabilities of adverse performance based on the variability among the point measurements. That's why you get these coefficients of variation of 40%.
Yes.
But I mean, if the coefficient of variation of the operative soil properties was that large, we'd have failures all over the place, and we don't, right? So scale is really important. And that's one point. And sometimes that bites you in the behind. If you look in rock mechanics, you've got this issue of joint wedges. And in that case, it works exactly the other way, because you're concerned about the most extreme orientation, in which case the larger the volume, the worse off you are, not the better off. So no, I think you put your finger on an extremely important problem, but outside the scope today.
Is that Otis?
Yes, it is.
All right. Please speak up.
Very much enjoyed your presentation.
Thank
My
you.
question, your comment about the insurers and assessing risk just leads to this. Who do the insurers look to for assessing risk for the owners of projects such as Tonin? And is this a market for geotechs who I would assume would be giving them some assessment of that risk so that they could appropriately price?
Yeah, I've got a couple of answers to that, one encouraging and one disappointing. The disappointing one is that market has already been kind of occupied. There was a company about 10 or 15 years ago out of the civil engineering department at Stanford, which many of you probably know about, called Risk Management Solutions. And Haresh Shah was one of the founders of that company. And they created a company which is now, well, it's subsequently been sold, but it's huge consulting, that consults to the reinsurance business, the Munich Re's, the Swiss Re's, the AIG's, the Berkshire Hathaways. And they went into business of trying to replace the old actuarial statistical approach to catastrophic loss with engineering models. And they started in seismic, and that was very successful. And they grew and they grew, and they finally got sold. But now a lot of the big reinsurers, of which there are only, people don't realize how limited, Mark, you probably do, how limited risk capital is, insurance risk capital is in the whole world. There are only a half a dozen really, really large reinsurance companies. And they have begun to take this engineering in-house. And so that has sort of cut the market for some of those. So there's 3 or 4 of those risk engineering companies that started about 15 years ago. On the other side of that coin is that, you know, a lot of, I mean, I work a lot in hydropower, and those companies all have, you know, risk analytic groups that, you know, create these numbers which they then share with the insurance companies in order to negotiate rates. But I think you're right. I mean, I think there's a definite market for engineering consultancies along the lines of risk management solutions, and I think one might look at the history of that company as a kind of a, you know, a lesson for how that has been done. But I will say that we have worked a little bit with the insurance companies over the years, not a lot, and they're very conservative, right? I hope there's no one from the insurance industry here before. Oh, are you? Okay, I'm sorry. I won't say that. Oh, you're not from the insurance industry. Okay. Yeah, okay, hold on just a second. They're very conservative. They don't spend money very, very readily, is my experience with them, and they have been in-housing a lot of this because the big reinsurers are in a really critical position right now with climate change. I mean, they're losing, some of them, not all, some of them are losing a lot of money. And every time you get a Hurricane Ian come across with correlated risks, right? I mean, if you're insuring houses in Sanibel, they're all going to get damaged. It's not like car insurance where you have a wreck and I don't, right? Or vice versa. So I think it's a period, I think it's a period of transition in the insurance business, which may, who knows? It's, I'm beyond that in my stage of the career, but if I were younger, I'd probably be chasing it.
Thank you, Elful.
I'm sorry.
Question.
Yeah, I'm trying to understand better your approach of statistics going forward. The approach of you have a bunch of data, and the first step is this average it out and get a standard deviation for it. You're saying stop doing that altogether. Did I understand this right?
No, no, I didn't mean something as extreme as that. What I meant is that the traditional statistical metrics and measures like confidence limits, p-values, if you're familiar with that, hypothesis tests, those things are really all broken. And it's not, I mean, I may be one of the few sorry people in geotechnical engineering who says that no one wants to listen to me, but if you look at things like the big federal agencies and clinical trials, the pharmaceutical companies, I mean, the insurance companies, I think a lot of people are beginning to realize that. There is something going, if you're not familiar with it, there is something going on right now that is really disturbing. It's called the crisis of replicability. Does that mean anything to you? Okay. And if you're not familiar with that, you might go Google it, because in many people's opinion, including very big names in the statistical field, a lot of that crisis is caused by sort of the traditional statistics answering the wrong questions. And I think there's no place where that is more clear than in geotech, because what we're really concerned with in geotech is the probabilities assigned to states of nature, right? To soil properties, to discontinuities, to storms, the probability of a storm, not just the return periods. And the math can often lead you to very different numbers in those two cases. So I'd be happy to talk about that over drinks for the rest of the afternoon, because it's one of my bugaboos, as you can tell.
Very good.
Yeah.
Well,
thank you.
thank you. Hold on a second. So we have a certificate of appreciation to Dr. Gregory Baecher, delivering his 2021 Terzaghi Lecture at the occasion of the 30th Buchanan Lecture, and it's signed by Dr. Graisley and myself. Thank you so much.
Thank you so much. It's a pleasure to be here.
Thank you very much. Now it's my true pleasure to introduce Dr. Mark Buchanan. After studying construction science at Texas A&M University, Mark Buchanan advanced through various management construction positions in heavy civil infrastructure projects, where he gained practical insight and experience in literally every aspect of the profession. His project assignments increased in scope and size and took him to multiple states and countries on projects for over 20 state departments of transportation, the U.S. Army Corps of Engineers, the U.S. Department of Defense, the U.S. General Service Administration, and various military branches. Ultimately, Mark recognized the need for a more advanced education and attended and graduated from Ventura Santa Barbara College of Law in 1997 with a Juris Doctorate. So he's got a foot in civil engineering and a foot in legal knowledge. Dr. Buchanan is particularly adept at risk mitigation, which is obviously of significant interest to the business side of both heavy civil construction as well as geotechnical engineering. His experience with the ever-increasing mega project sizes, coupled with the changing dynamic introduced by modern construction contract platforms, in which contractors, as opposed to owners, are increasingly in privity with the engineering community, is one of Dr. Buchanan's focused practice. Over the last 40 years, Mark Buchanan developed distinctive competence in business and construction leadership with successful results in heavy highway power generation and industrial construction under a broad assortment of construction contracts platform and delivery methods, included but not limited to bid-built, design-built, construction management at risk known as CMAR, and public-private partnership. He successfully performed as senior vice president and president of several large-scale publicly traded heavy civil engineering firms. Collectively, he's had direct management responsibility for well over $14 billion in construction revenue. So as you can see, Dr. Buchanan has an impressive resume. It is somewhat different from our past Buchanan lecturers, but it brings a breath of fresh air and a look at the bigger picture. Mark is also the grandson of Spencer J. Buchanan, after whom this lecture is named. Professor Spencer Buchanan started the geotechnical engineering program at Texas A&M University in 1946. At the time, it was called Soil Mechanics and Foundation Engineering. I came to Texas A&M University in 1978, and Professor Buchanan died in 1982, so our paths did not cross for very long. But I do remember one instance when, in 1981, he came and talked to our students. He was a storyteller, like many of the giants of that time, including Peck, Seed, Meyerhoff, and more. He stood in front of the students with no slides and just described the case history like he would tell his children around the fireplace. Everyone was glued to his words. Spencer and Mrs. Buchanan had two sons, Philip and Spencer Jr. Philip was a local, but Spencer lived in Guatemala. They came together to the Buchanan Lecture in 2006 and told a story I'll never forget about buying a second-hand car that was in very bad shape and how they brought it back home. They dragged it back to College Station at night with no lights because the battery wasn't working. All this unbeknownst to their father, who wondered where they were. When they got home very late that night, Papa Buchanan was very, very upset. But Mama Buchanan managed to smooth out the problem. Mark is the son of Philip Buchanan, I've known Mark for a good while now. I've always admired his sense of civility, his kindness, his positive attitude, and his very practical approach to all problems. I count him among my friends. It's my pleasure to now invite Dr. Mark Buchanan to deliver his 2022 Buchanan Lecture entitled Risk Mitigation in the Changing Relationship Between Contractors and Engineers.
Well, thank you, Dr. Briaud, for those kind words. It's both an honor and a privilege to get to be here, obviously, to be able to participate in my grandfather's legacy is tremendous. There aren't words. When Dr. Briaud called me several months ago to ask me if I would participate in the lecture, the Buchanan Lecture, I was at once flattered and intimidated. Flattered for obvious reasons, intimidated by virtue of the fact that I was looking over 29 years, and this is the 30th, and the caliber of the lectures over these years is extraordinary. And also, I was intimidated by virtue of the fact that I'm not a geotechnical engineer. I don't have any expertise in geotechnical engineering, other than I'm fairly intimate with Proctor curves, moisture, getting density. My focus throughout my career really has been in construction. So as I reflected on coming here today, I thought about my grandfather and I thought about Dr. Briaud. And just a couple of comments. I looked up the word legacy. It obviously has some Latin origins, but in the 14th century, the French, appropriately so, or perhaps by coincidence, they began to interpret the word legacy somewhat as persons sent out on a mission. And metaphorically, that was more akin to appointing a spokesperson for the future. Obviously, Dr. Briaud has been an extraordinary steward of the Buchanan Chair. 30 years is an awful long time to perpetuate a legacy. He's also a tremendous ambassador for Texas A&M University. The traits that I notice in Dr. Briaud, a true passion for engineering. Obviously, with the type of achievements in his career, he just loves what he does. A tremendous ethic, a very tremendous work ethic, but you know, when you have a passion for what you do, work is not work, it's fun. And also, he's incredibly humble. I was speaking last night with a graduate student, very nice lady, and you know, she mentioned no matter how big or small, Dr. Briaud was always available. And I had the same experience as he helped me with my PowerPoint. So thanks again, and everyone's taking the wind out of my sails for the applause, but I just can't help it. Thank you. And so then I reflected some on my grandfather, obviously. Similar traits, a true passion for service, a true passion for engineering, a true passion for society. There's a story that I'll tell very quickly. He was in the military, and he made general in the military. They offered him additional stars if he would step away from the Army Corps of Engineers. He declined the offer. He didn't really care about being a higher ranked general. His passion was in engineering. He did not want to step away from the Corps of Engineers. Tremendous work ethic, both in terms of the office, but also in terms of the student body and his fellow citizens. And tremendous humility. I never heard my grandfather speak ever about any of his achievements. But on occasion when I was attending A&M, we would go out to dinner once or twice a week, my grandparents and I, and we would sit down at a random table, and throughout the course of the evening, several people would come up, and it wouldn't be unusual that a dozen people would come up to pay their respects to my grandfather. In true gentleman style, he would stop eating, put his napkin down, stand up, take whatever time it took. So going out to dinner with my grandparents could easily consume an hour and a half, 2 hours. But he definitely was a true Southern gentleman in every positive sense of the word. So we'll get into some of the fun of it now. We're going to do 3 case studies fairly quickly, but first I need to lay a foundation. This particular picture is not from a design build, but it emphasizes the point that you've got to plan to build and build to plan. And I think this is central to constructors as well as engineers. But let's kind of set the foundation for design build and some of the risk and some of the dynamics that have changed. I'll start with, in my opinion, the construction industry has changed more in the past 10 years than in the past 50. It is a very fast-paced, changing profession. Geotechnical is a tremendous part of this change, and it affords major opportunities. If geotechnical engineering is your passion, then you are absolutely going to be incredibly successful as long as you couple it up with a work ethic, which won't be hard if it's your passion. There have been some changes over the years. 50 years ago, the constructors were really the blue-collar guys. They were the folks that went out there and did their best that they could to emulate what was in the design and build it. We'll talk about why there's been an evolution there. Most of it boils down to money. It's a tremendous amount of money, tremendous amount of risk. These historical perceptions are changing, but so are the contract platforms. And I think it's a very good thing, because back in the day, engineers would frequently work for owners. Owners being state agencies, municipalities, counties, state, federal. As the advent of design build gains increasing traction, the engineering profession is working more and more with the contractors. This is fostering a mutual understanding of the profit and loss, the business approaches, and ultimately, I think, renders projects with tremendous innovation and a much faster delivery time. I would be remiss not to address generational dynamics. When you're on the professional side of work, when you have an executive management position, you've got to be cognizant of your profit and loss all the time. How do you do that? It's not a slogan. These big construction corporations and engineering design firms, I was having a brief discussion today. It's all about recruiting and retaining the best talent that you can find. And given the pressure of profit and loss, it's not about throwing money at it necessarily. It's about understanding the generational changes. I'm a baby boomer. I'm the guy who my parents said, children should be seen and not heard. But you won't find a Gen Z who's ever heard that before. They have no concept of what you're talking about. But there is a mutually reciprocating benefit by understanding these generational changes, because the Gen Zs are bringing remarkable technology and they're leaving us old guys behind. And so it's critically important as we all look forward in the business model to understand, the baby boomers and the Gen Ys or Gen Xs, I should say, Yeah, they're in leadership roles. But the Gen Z people are really bringing a lot to the table very quickly, and it's critical to understand that there's needs to be a mutual commitment to success. It's anybody that's in the business and that is concerned with profit and loss and is concerned with risk mitigation should be cognizant of these. You know, the academic people, the professors, they get to deal with the students all the time. But the paradigm is entirely different. Why? Because you guys are paying for this. You're paying for the mentorship and the education. That the paradigm changes entirely when now all of a sudden you're out in the professional world and you're getting paid, but with that you have certain expectations. So there's a commonality that's coming up in the emerging contracts, and they're listed here. You know, design build really is a component of many of these different contracts. I put design build on top, but there's CMAR. Frequently design build is a component of CMAR. Public-private partnership, that is oftentimes a design build. It involves a concessionaire contract. Generally, it involves financing. So basically, that's a situation involving educational institutions, hospitals, highways, mass transit, in which the owner may not have the funds, but they want the project. And so what they'll do is they'll set the contract out. The developer or consortium has to come up with the money to build the job. They engage the design build component to build the job. They put on the trains, they do whatever, they run the project for 50 years. They get a percentage of the revenue. I'm thinking of one just south of Houston. They get 80% of the revenue for 52 years. It's not very attractive to United States companies. It's very attractive to international companies. We could talk about that for hours. But the bottom line is that we're seeing more and more triple Ps. All of these involve design build. On a triple P, design build may just be 15% of the contract. The contracts are massive. They would fill the room, almost literally. They are massive because it's right-of-way acquisition, it's finance, it's concessionaire, it's operations. They're very, very big contracts. And so the design build component is minimal. And the reason I point that out is that if you're an international company and you want to get into the US dollar and you want a revenue stream for 50 years that's in the US dollar, you might not be that competitive on the design build portion because you're in it for the long haul. You're in for the return over a 50-year period. What drives this change really is money. And it influences all of us all the time. It influences the graduate students. What is the driving force behind your thesis? It's grant money. How do you select which program you want to be in? It boils down to money, and it'll follow you right through your career. It has an influence on the owners. What is their interest? Well, they want a project. They want to get some infrastructure in place. They need it quickly. They want to mitigate their risk. Common perception, it's not always true, generally true, that if it's a design-build job, they're mitigating risk. It's not their design, it's not their construction. They're mitigating risk. They'll get innovative ideas. They'll get the project delivered quicker. But they're all through the course of this, they're mitigating their risk. It has a big influence on the new contract platforms we're seeing. It has a big influence on the industry profit and loss. Why do I say that? Well, because in a design-build format, by the time you're bidding the job, all you have is a conceptual set of drawings. You're bidding on a concept and hoping that it's going to work out. So you develop a risk register. You generally, on a bid build, a traditional bid build job, you'll have a risk register that may be 8, 10%. If you get into a design build job, that risk register changes quite a bit. because you're getting increasingly concerned about your relationship with the owner, your relationship with the engineer, your relationship with a joint venture partner, and the fact that you're basically putting together an estimate based on a concept. You never even see 30% design by the time you're bidding these jobs. So you're rolling the dice. It's definitely professional gambling. And with that comes a contingency, right? So I'm going to focus today on heavy civil design build. That's really where I've had most of my experience. Personally, I like heavy civil. I find it more challenging than energy or petrochem, water, wastewater treatment. And they're all very interesting and they can be quite complex. For me, it's easy to look at a highway and think about how simple it is, but when you actually roll up your sleeves and get involved, I love the complexity, I love the size of heavy civil work. The airfields, the dams, the complex interchanges, the tunnel bores, they always intrigue me. I love that kind of work. In a heavy civil design build, generally there's a pre-qualification period. So the owner will put out a solicit a bid, we're going to build this job. And contractors and engineers will team up and they'll submit a statement of qualifications. It's a pre-qualification period, and the owner will generally select a few, 2 or 3, who can go ahead and move beyond the pre-qual period and actually submit a bid. The reason is because, again, money. It's very expensive to put together a pre-qual and a proposal on a design-build job. So the owner will limit its financial exposure by selecting, let's just say, 3 of the 5 or 6 people that have submitted a statement of qualifications to move on through. And the process is based on experience, financial solvency, all sorts of elements. Through the SOQ, if you're approved to go bid, then generally the contractors enter into a teaming agreement with the engineers. The teaming agreement is a fairly loose document, and I'm critical of loose teaming agreements. And case example 3 will point out acutely why. But the engineers go in through the teaming agreement and the conceptual design generally at 0.5%. So it is not much money to, frankly, work your tail off in a very compressed period of time to try to put something conceptual together that's adequate enough to submit a bid. So let's just say you're on a $200 million job. You're going to put together a package suitable for the contractor to develop a bid for $750,000 to $800,000. And you're going to do that in 3 months. It's quite a challenge. It's not an easy task. So we'll talk more about the teaming agreement and contract platforms. But if you win the job, you submit your proposal, you win the job, you're successful. Now the engineer community is going to go into a design agreement to go ahead and take their conceptual design into IFCEE or RFC drawings that are approved to go and construct. Generally, they're going to get 6-7% of cost to construct. So, $200 million job, $11-12 million. That's their total fee. That's not their profit, that's their fee. But again, you're in a fast-track environment. You've got to be very, very cognizant of an awful lot of things because the contractor's just bitten off, let's say, a $200 million job. So they need to move through it quickly and fluently. You got to really know the parties. To be successful, especially in a design build or a joint venture design build, you really have to know who the parties are. What do I mean by that? We'll get into a tad more detail, but you got to understand the cultural differences. You got to understand what their motivations are. What's their backlog coming into this? are they running really light on backlog, and do they need revenue badly? Is that going to influence them to put in a lower dollar bid to go get that work? If the engineer's fee is based on a percentage of the cost to construct, the engineers need to pay very close attention on the estimate. Oftentimes, the contractor will say, oh no, that's proprietary. That's based on our historical data, and we're not going to share, you're not going to be in the room in the final bid. I'd be a little cautious of that if I was an engineer, because my fee is tied to what that cost is. Know the schedule. Okay, this is critical on the engineer side. Understand that schedule. Understand that schedule. It'll frequently be in the design agreement. Understand what kind of resource loading you need to put on that schedule. It's very, very important to the contractor. Ultimately, it'll be very important to the engineering firm, and we'll examine one or two case studies of how that hurt. Once again, know the plan. Plan to build, build to plan. The best, most successful contractors out there, they're going to have a plan. That plan is way more than the design. That plan is the traffic control plan. That's the schedule. That's the design. That is how they're going to go and put this project together. And why is it relevant to the engineers? Because you're fast tracking through the design. So you need to fundamentally understand the core design and then fast track each one of those components for delivery in time that it does not impact the critical path of the contractor. So I frequently get involved in joint ventures and design builds, and I'm always sitting down with the engineer right up front saying, I don't know what you guys know about P6, which is the scheduling format we frequently use, but you need to know a lot about P6. So you can find one, or I can help you get one, but understand the schedule. I've already hit on participate in the estimate some. And this is the hardest part of my lecture. After this slide, I get to get in the case studies, and I like that an awful lot more. Cost-benefit comparison, engineering and contracting. Again, we've touched on. Engineers get 6% of cost to construct. So out of that, let's just say that we're talking about a $200 million job, and the fee is $11.5, $12 million. If they pull down 10%, 15%, all right, so you're at $1.5 million, $1.6 million in profit to go and build this $200 million job. The model is a little bit different from the contractor's perspective because they just bought off a $200 million commitment. Now, in today's money, $200 million really doesn't sound like that much. We're going to go into a case study that's pretty interesting, and it's quite a head turner. But it's a $200 million commitment to go build based off a conceptual design. So they're on the hook for an awful lot. Because of this dynamic and the ever-increasing size of these projects that we're seeing out there, contractors have been forced to become much more sophisticated. My colleague from Kiewit, he's a geotechnical engineer. He manages a number of geotechnical engineers. It's not uncommon for the big, heavy civil carriers to have quite a bit of staff. And the best ones are civil structural combinations. I always have several engineers available. They are best equipped to communicate with the engineering professionals that are bringing the design side to the table. Difference in business models entirely. Generally engineers work on a personnel labor rate plus a modifier. It's, and expenses, right? So you'll see the modifiers all the time. The low end these days is 1.7. The high end, 1.85, 1.9. It depends on the complexity of the design that's coming out. But it's really, contractors would almost call that a T&M type of deal, right? It's time and materials, and you're paying on a modifier to get to the end game. Conversely, contractors are lump sum at risk, generally. And there's all sorts of platforms, all sorts of different perspectives on it, but the trick is to get to reconciling these different professions to a successful outcome. And So I'm going to provide, look, there are lots of very positive examples of design build. And personally, I'm not so much an advocate of the public-private partnerships, but I'm quite an advocate of the design builds. And we see more and more of them. TxDOT, frankly, is lagging, but they're catching up. Design build is a great platform, and I like it because it changes the relationship between contractors and engineers in a very positive way. If you can develop that relationship that is collaborative, cooperative, you really can come up with, the engineers get the benefit of understanding that a contractor, the two things in the back of a contractor's mind constantly are time and money. And those two things are never in the back of the mind of most public agencies. They just don't have the same budgetary drive or time drive. And so it's quite revealing, I think, sometimes for the engineering community, because almost every sentence that goes by, it's either touching my time button or my money button, right? The engineers bring very insightful professionalism to the contractor's table in a design build. And so I think as time goes by and there's more collaboration and more cooperation between the professions, we're really going to see some dynamic, innovative projects. I'm just a transient construction worker. I am not, I've been fortunate over the years because I have a passion for building. As a child, I always wanted to build stuff, and now I just get bigger toys, right? I don't want anybody to be negatively influenced by some of the case examples, because there are many, many positive examples of design build. But I learn best from my mistakes. And so I'm going to bring out a couple of projects, and certainly one or two of these I think I've shared with civil engineering before. The third case study I'm going to really wake you guys up to, and I guess I'll wait until we get there. So this one was the Fort Lauderdale Airfield expansion. It was a design build. It was between a contractor and an engineer that had worked together on many projects. So that relationship was already there. That relationship of trust and accountability is critically important. It was a good job. It looked to be a great job. It had some prescriptive specifications in it. The runway is going to be north-south, clearly. But it also had design performance specification aspects of this particular contract. And there was a success fee. We'll go into what a success fee is in a minute. Personally, I'm not a big advocate, and after I get done explaining, you might see why. The parties did all the right things, really. They agreed to co-office. Once they got beyond the SOQ, they co-officed all the way through the proposal phase and then through the design IFCEE, RFC phase. And that's a very good way to go about doing a design build, because when you co-office, you interact daily. You have scheduled meetings every single day. You have over-the-shoulder reviews, constructability reviews. It's a very smart way to do a design build. And there was some measure of foresight, but we're going to examine what happens when you kind of get wrapped up in the forest and overlook some critical elements. At the end of the day, although this was a tremendous relationship with the engineer, I don't know where the final number settled, but it was around $20 million that the engineer had to come up with. And so it was devastating financially. Great engineering firm, I think very highly of them. They recognized what the issues were. So what I like so much about this particular design build job are the nuances. Okay, so it's always a challenge to go pour a runway. You've got an 1.5 inch slump. You're trying to leave a ride, an IRI that's tremendous. You know, you're pouring a 12 to 14 inch keel. Runways are fun and they're challenging. But this particular project had special challenges. Again, I mentioned the design performance specification. So initially, the owner lets out a specification. You can see where the jets are landing. They're landing on structure, okay? They're landing on what I'll loosely term underpasses. We'll talk about what that is in a minute, the difference between an underpass and a tunnel. But you can tell where the jets are landing. That's a fun challenge right there. The owner had a performance spec for a 747-800 jet, okay? So everybody's going through the teaming agreement, the pre-award, the conceptual design, and we're all putting it together based on a 747-800. 5 or 6 weeks prior to the bid, the owner amended the performance spec to an Airbus A380. We'll talk about some of those details in the next slide. The success fee. A success fee is designed to motivate the engineering team to come up with these innovative ideas and to help the contractor minimize what's in the risk register and the contingency at the time of the bid. So in this particular case, the engineer was going to get a $500,000 success fee from the contractor if the contractor was low and got the award. And that's exactly what happened. So this is a better view. Here you are on close approach. You're in your little airplane, and look at where you're landing. I mean, you are landing right on these structures, okay? So let's talk about this performance spec. 747-800, it weighs 495 tons. An Airbus A380 weighs 589 tons. So you're almost 100 tons heavier coming in for a landing on top of these structures. It involves 3,600 piles. So when they amended the performance specification, the contractor kept going back to the engineer. We good? Are we good on these piles? Yep, we're good. Okay, well, this isn't going to be an oral conversation. Here's a letter. Are we good on these piles? Yep, we're good. 3,600 18-inch by 18-inch piles. We bid the job. We got the job. $500,000 success fee goes out the door. Engineer comes back and says, oops, we got a mistake. Those piles are going to have to be 24 by 24. All right, so 18 to 24, I'm not very good at math, 25%. No, not exactly. 33% bigger piles. So think about the complexity for a minute. Now I'm going to step into the geotechnical world. You're in Fort Lauderdale. It's sugar sand. Your water table's right up on top of you, and you're driving 3,600 piles in very close proximity with one another. Pap-wap all over the place. You're analyzing these piles, and it's very much an art because you're not going to hit a point of refusal. You need to find that perfect interaction, and then you got to leave the zone entirely and go drive piles someplace else, wait 7 days. Now let's see what it does. Boom, it's holding. Good, you got your skin friction, you're all set to go. But these piles are 3 feet away from one another. So it was a huge engineering and construction challenge to drive 3,600 piles, 24-inch by 24-inch piles on such tight centers. It was quite the deal. And the additional cost, again, I don't know what the settlement was, roughly $22 million. So the second issue, and this is kind of watching the forest for the trees. Consider the length of these tunnels. and look at, okay, well, I can understand, you know, you're going to span directly across. You're not going to put the beams on a skew. All right, I get it. We can build that. Especially look at this edge of the runway. This is mandated by the FAA. That's what they had to be. You had to have that much distance. So the design goes in. We get the RFCs, Contractors Build in America. All of a sudden, the fire protection people show up. You know, that isn't an underpass. That's 835 feet long. Anything over 800 feet long, that's a tunnel. Okay, well, what difference does that make? Well, now you're using turbines for the exhaust. Turbines are really expensive, over 35 feet. So kind of my point here is I always keep an eye toward the end game, the long game. What are we doing? Because so often we get kind of interested in the puzzle, and we're going to solve this puzzle, but we've got to drop back and keep a perspective long term about what happens if we just go straight across instead of running it askew. Okay? Now, maybe from an engineering perspective, these beams are very close to one another. Maybe on askew, the beams are too, I don't know. But what I do know is that going to turbines was about $6 million. And again, this is just consider the skew. This gives you a little better perspective of what the lengths of these underpass transformed to tunnels ended up being. So the takeaways here, take the performance specs very seriously, especially if one shows up in the 11th hour. Maybe I'm not cynical, but maybe I'm just very cautious. If some addendum shows up 4, 5, 6 weeks, I don't know if there's an ulterior motive or not, but I can guarantee you that I'm paying really close attention to design build addendums that show up in the 11th hour, right? And also stay cognizant of the big picture. I apologize, I'm trying to kind of accelerate just a little bit because I've only got an hour. The other one is the Alaskan Tunnel Bore Project. It's a big project in Seattle. I say big at the time, pretty good size, $1.4 billion. This is more of an example of contractor error. There was one minor thing that we're going to talk, I say minor in relative terms, with respect to the engineers, but this is a great project. I love the tunnel bore projects. This one was particularly challenging. And in this one, I want to emphasize, look at the nature of the joint venture platform. This one had a majority joint venture partner, international, with a minority national. And the cultural differences really came to light quickly on this job. And the way that a lot of JVs are handled in a broad assortment of different ways. Sometimes it's just a financial arrangement, and one of the partners is going to build the majority of it. Sometimes it's a need to have a local partner because of certain advantages you would get from a DOT in a given state. Sometimes they divide it by scope. In this case, they divided the work by scope. So the international managing partner was going to take the mining. They were going to take the tunnel bore. The national minority partner was going to do everything but the mining. The engineer got involved with the secant wall. We'll talk about that. That was the one little fly in the Chardonnay on the engineer side of it. The contractor, in my view, really failed to fully grasp and understand what the tunnel bore machine, the TBM, how to best interact with glacial till. And in my super layman terms, when I think of glacial till, I think of huge glaciers and they're crushing everything underneath, but the round cobble that they leave behind has got to be the hardest stuff that I can imagine, right? So I'm sorry I'm not a highly technical geotechnical engineer, but I can tell you one thing. The glacial till, that is really something to reckon with. Accountability. You know, nobody's perfect. There's no such thing as a perfect design. There's no such thing as perfect execution in the contract. But the traits that I saw in my grandfather and I see in Dr. Briaud, ethics, accountability, it's critically important for the long-standing relationships that every party to every contract ever, if you deal with one another with an equal level of commitment towards success, and frankly, I carry this in my personal life, equal levels of commitment create the best relationships that you can have, personally, professionally, anywhere. When you get involved in a big multi-million dollar, $1.4 billion, it's sometimes easy to overlook accountability and ethics. So I'm going to whip through a couple of pictures fairly quickly. I kind of like this picture. Here you can see that the tunnel bore entrance has been developed with a secant wall. You can see the modules from the tunnel bore machine. At the end of the day, the tunnel bore machine is 360 feet long, roughly 60 foot in diameter. At bid time, we put in $50 million for this TBM. Ultimately, the managing partner, of course, who had the mining, wanted the more Cadillac TBM. It was $82 million TBM from Japan, largest of its kind at the time ever built. Very reputable company. And it remarkably has one use. And you'll find in many tunnel bore jobs, the owners are always going to specify you get to use it one time. Just a couple of pictures to walk through. There's the one module of the TBM showing up by ship. It's critically important to offload those ships right away. The demerge is incredible, and if you don't get right on it within 3 days, that ship goes back out to sea. Another fairly interesting shot of the module. So I don't know if you can see them very well, but these are the trucks or the rollers that the TBM actually goes through as it creates the tunnel. There are 2 conveyor belts in this TBM. One extracts the soil and the excavated material. The other one brings in precast concrete panels. They are pneumatically grabbed and set in place. An entire ring will be installed. The tunnel bore machine reaches out and literally pulls itself forward. All right, the cutter teeth on the gear. So that's what it looks like. It's beautiful when it came off the ship. We basically ended up having to replace all the cutter teeth 1,000 feet into the mine. It should have gone all the way through. That was the first red flag. Why are the cutter teeth going away so quickly? This machine's not designed to back up. It only goes in one direction, and it's forward. So backing up this TBM, to get access in there, and of course you're mining, so you're MSHA, not that we would ever ignore any safety requirement, but the safety is very intense, and you've got to figure out now how to back up this TBM and replace the cutter teeth. The cutter teeth were the cheap part of the deal, $4 million. Okay, so we get it all done. The majority JV member goes back to mining. They get about another 500 feet in, and they quit working. So everybody was breathing a sigh of relief. You know what? It's still under warranty. So the manufacturer shows up, and they had their nice pressed white jumpsuits and briefcases, and they all arrived to this TBM, and they pulled out 6 boxes. Black boxes, not unlike black boxes you'd find on aircraft. They record every input, every pressure, everything that's going on with that TBM as it goes through. Well, the TBM was operated outside the manufacturer's recommendation, no warranty. Now what? You've got a TBM that's underneath downtown Seattle. You have to excavate 120 to the top of the TBM. You have to figure out your shoring. You have to excavate down. You have to pull off the cutter head. And guess what, man? They don't have cutter gear sitting on the shelf. So you have to have new gear, put it in, put back the cutter head. It took 2 years at $100,000 a day liquidated damages, constantly clicking by every single day. So here's the entrance pit. This was kind of really, I mean, there were abundance of engineering issues, but I gotta say that the engineering teams worked really well with the contractor team. This issue caught them by surprise. The secant wall for the entrance shaft. You can see, well, I guess it's really difficult to see in this picture. The diameter of the shafts is really large, too large. The engineers got behind on their delivery schedule. What did they do? They threw in a 5-to-1 factor of safety. Well, okay, we had no choice but to go, Daddy, go and build it because the tunnel bore machine was on the ships coming across the ocean. There was a delivery schedule. But the point is, stay very, very cognizant of delivery schedules, especially in design builds, because there's a lot of money at stake. And jumping into a 5-to-1 safety just to kind of get something out there, okay, well, that may kind of solve the immediate problem. But the contractor's likely to come back and say, look, that costs an awful lot of money. So I'm going to fly through a few pictures. There you are, putting in the belly. You can see the secant wall. Obviously, there's a good deal of hydrostatic pressure going on here. A lot of tiebacks involved. A very interesting forming system to get that concrete at that shape inverted and trying to keep the forming system from floating. I particularly like this picture because there's the Seattle Seahawks Stadium in the background, so it gives you an idea of the close proximity right there at the wharves. You can again see the belly. There we are putting it together. You can see that the concrete's almost done. There's a little bit more to do right in through here. You've got the gantry crane, a Manitowoc 999, which is always a fun crane to be around. You can see several of the modules all staged and ready to go. This next picture, the TBM is now basically put together. It's 360 feet again. So I'm going to stop on this one. I always like this picture. It kind of gives you an idea of the magnitude. So what's happening inside this tunnel is there's a double deck of 2-lane highways. There's a lower deck with a highway, and they're separating, and a highway up on top, 2 lanes each way. I've already gone over losing the cutter teeth at 1,000 feet, losing the seal at 1,500 feet. Why did they lose that seal? Okay, well, we've got an idea from the manufacturer, but what did the majority contractor say? Well, it said that we hit an undisclosed thin wall piezometer pipe. All right, well, look, steel is not good on cutter heads, I get it. But a 10 or 12 inch thin wall piezometer pipe really is going to stop that machine? But frankly, that's all they had, and they ultimately claimed against WashDOT for $642 million. And then mysteriously, the evidence kind of disappeared, and that claim dropped down to $337 million. And WashDOT recently was awarded $57.2 million for the delay. But what this doesn't address, this is all money and this is all lawyers coming to the table doing their deal. What it doesn't address is 2 years of delay and a loss of time in the public eye. You start to lose confidence when things like this happen. So then the minority contractor gets to do his deal. You can see that he's got his rolling gang forms. He's going to move through and build the walls. I say he in a very gender neutral way. we had quite a team that involved a bunch of men, but a bunch of ladies who were very competent on this job. So we have this rolling gang form system for the walls. This is where the tunnel bore finally came out. That's a little better picture of the gang form system. You can tell what they're doing with the walls. You've got your dowel bar projections for the upper deck. You can see the dowel bar projections. The walls are now done, and we're working on the roadway entrance, so the approach and departures for the actual structure. There's the upper deck going in. Getting close to done here, and there you go. The beauty of this really for the downtown Seattle is that the existing elevated Alaskan viaduct was right on the coastline. And once this was put in and activated, they were able to demolish that bridge, which was in serious structural jeopardy by virtue of the earthquakes and seismic activity. And now it's all a park. So when you go to downtown Seattle, it's just stunningly beautiful, anywhere from downtown to look down to this area. And it's, you know, it took too long, but it's nice. Lessons learned, and then I'm going to move into the one that I really am concerned about and would like to share today. Okay. The engineers need to stay really cognizant of the schedule. The only real fly in the Chardonnay was getting the sea camp walls in there, and we spent a lot of money on the entrance pit. Contractors should very well understand their JV partner, and what I'm talking about there is understand the cultural differences, understand what the backlog looks like. Are they in need of additional work? How are they doing? Look at how many different JVs they've done with the same partner. That's a very telling thing. I mean, examine these things, because if you get involved, you're going to be involved for the duration of the job. And tough jobs they don't get easier, right? They get over with, but they don't ever get easier. The third one I wanted to talk about, and I've got to be very careful here because this one's in litigation. I have a passion for operation. I have an affinity for some of the legal aspects of these things. I don't take very many files. I took this file because it involves a well-known, well-respected engineering firm, North American engineering firm, although they're international. It involves an international design-build contractor. The bid went in for about $200 million. Cost to construct exceeded $500 million. And the contractor wants to blame the engineer for everything. And so I have a personal interest in this because I think it really matters to design build, because obviously if this litigation succeeds, it's going to be very difficult for engineering firms to get E&O insurance to play with any design build, and I'm an advocate of design build. So it kind of started with a teaming agreement. Teaming agreements generally are placeholders for a design agreement if everybody's successful. And so teaming agreements don't get the same level of attention that a design agreement might get. Teaming agreements should address liability straight up. What are you doing during the teaming agreement size? You're developing concepts. You're not developing issued for construction designs. You're developing a concept that the contractor can bid on and move forward with. Emphasize that and limit your liability for what you're doing. Pre-award design management. So they come into this $200 million, actually, I can't get too detailed. So let's just say $200 million job. What's the teaming agreement generally? 0.5%. Let's call it $800,000 to $1 million. Contractor didn't want to pay that. So they decided that they would go time and material. This is another thing that I would not do as an engineer. So you have all of these design scopes that are available to go do, and the contractor is treating that like an a la carte menu. Here's what we need to bid this job, and we will pay you under T&M to get this done. And they're all about trying to save money. They felt like $450,000 was a reasonable fee. Wasn't. Making matters a little bit worse, their design build coordinator was not an engineer. So the guy had some construction experience, but he is telling the engineer what to do and what not to do. And consider the standard of care, right? How do you reconcile that? The bid circumstance. Contractor had low backlog. They needed revenue badly. First flag. 11th hour changes. Why was that? Well, because their estimate of cost was above the limit set by the owner. So all of a sudden they're doing what they call green sheet costs, coming up with design concepts unvetted and taking the benefit of those design concepts that had not been checked at the time of the bid, okay? Pushing that number, driving that number down. The number 2 bidder at the end of the day had $70 million more on their bid on a $200 million play and took 12 more months to get the job delivered. They treated the schedule specification more as something to go satisfy and check the box. Yep, met the spec, moved on. They never really developed a comprehensive resource-loaded schedule and stuck to that plan. Then they went into the design subcontract, 6% of the construction costs. All right, well, is that going to be 6% of 200 million, or is that going to be 6% of 500 million? Very provocative question, right? So was the engineer in the room when they were having their estimate review? No, wasn't invited. As an engineer, I would say, why aren't you in that room? Because they're cutting numbers left and right, and that's going to affect the engineering fee. But also, you need to have a measure of confidence that the engineer knows what the constructor knows what they're doing and understands what it's really going to cost. On this job, they went into it with less than 1% contingency for design. 1.6% for the whole job on a design build with a conceptual design. It's just unheard of antics, but kind of don't get too enthralled with the chase, right? So, conceptual nature at design, I always bear that in mind, emphasize that in the timing agreement. Please limit your liability in the design agreement. Don't think of, in the teaming agreement, don't think that it's a design agreement. It's not, it's a teaming agreement. Limit your liability as engineers. Watch that pre-award design, contract and liabilities. Get involved with the estimating process. You're always going to get some pushback. Oh, this is proprietary information. You've got skin in the game as an engineer, right? Get involved with the scheduling process. Have somebody on your staff that understands that schedule. Watch the updates. The updates are, watch that critical path. You're going to see it move around. Hopefully you don't see it move around too much, but it's going to move around. What's that going to tell you? It's going to tell you that your design deliverables may be moving around. Design subcontracts are all generally pretty good these days, and again, my mantra, plan to build, build to plan. If you do that, you have a much better chance of success. And I'll start to conclude. I like this picture too. It's not a design build, but the point of this picture, it's a beautiful segmental bridge. The water level here raises 120 feet every year. It creates unique design challenges because you cannot build these bents in time before the water's coming back up. So quite a feat getting the trestle bridges in place and putting together this segmental. But the conclusion is that hard infrastructure is really a significant market. I like it because everything's unique, everything is new, and I guess I got to admit I just like the big toys. But there are billions of dollars involved, and it's really horizontal construction. So from a geotechnical point of view, it's a lot bigger than the footprint that you're going to see in a skyscraper. You really get to spread your wings and get involved. The evolving relationship with engineers and contractors getting better and better and better every day, and it's really a pleasure. It's very insightful to me. Design build gives you the innovation speed, but you also get risk. And then I'll wrap it up. Understand the stakeholders. Understand their motivations. Why are they even interested in this job? Have a pretty good understanding of your own motivations to get involved with this job. Take a close look at the design coordinator expertise. Subcontract platforms, make sure you get the limitation of liability in the teaming agreement. Make sure that the teaming agreement has a relationship with the ultimate design agreement, i.e., we go into design agreement, the teaming agreement's done. It's superseded. It's gone. Active participation in the scheduling, active participation in the estimate. I'm referencing Read 1 and Read 2 here. Generally in a design build, if it's a joint venture, the two partners develop their estimate and their schedules ostensibly in a vacuum, and they meet together for Read 1 to examine one another's approach to the job and to try to reconcile differences. They come back for a Read 2 to see if they're tight on the number, and then they agree to go, right? To the extent it's possible, I would say, from an engineering perspective, get invited to that meeting and attend and pay attention. Understand the conceptual nature right at the beginning. Watch out for the success fee pitfalls. I really don't know what happened on Fort Lauderdale and how they became so enamored with success fee that they didn't consider 100 additional tons hitting the threshold of an aircraft. Watch out for the performance specification, especially if it shows up late. I love the co-officing. Really, it's a collaborative, cooperative team. If you're not together, working together, you're going to miss a lot of details that happen in a design build. Critical, I think, perhaps the closing is the most significant. Foster and develop a culture of collaboration, cooperation. Critical that you have trust and accountability right from day one. Thank you very much. Got any questions?
Any questions for Dr. Buchanan?
Easy crowd.
Question, go ahead.
So would having the contractor and the engineers under the same company, would that alleviate some of that risk that is associated with the disconnect between the contractor and the engineer?
Absolutely. Absolutely. Again, it's driven by, when you're on the private side, when you're on the, you're driven by P&L. You're driven by having safe, high quality, but at the end of the day, you're driven by profitability. And so I would suggest that if everybody's drawing a paycheck from the same entity, then almost by definition, but also there's always variables. But yeah, you're going to have a level of collaboration and cooperation and accountability because you're all under the same roof. So I would think so.
I have a question. The students here are geotechnical graduate students by and large. It seems that it's becoming very important to have some understanding of the legal aspect of the business. If you had to advise them, in the number of courses, or what courses should they take that would better prepare them for the kind of problems that you described?
That's a very good question, and I don't really know what the curriculum offers at A&M, But certainly, contract law, it's all driven by contract law. There's very little criminal law or tort law involved in these. It does get a little bit of detail when you're talking about the various liabilities and subrogation and all of the different insurance aspects of it. But, really, there's been a shift in the legal world away from real technical terminology. And what I'm seeing these days in construction contracts, it's pretty readable. It's certainly be sure that you're reading these contracts. I'm always dismayed when I'm working on the legal side of it and an engineer or a contractor's hired me to examine some turbulence, and I find things in the contract that they were unaware of. And they aren't hidden, they aren't hidden behind terminology. They're right there in black and white. So yeah, I would think that contract law is critically important, and also just take the time to read the contract. Yeah.
Any other question? Prince.
Like suppose the team of the design engineers, and if the contractor will not let them know everything about the project or in the future, so how they will deal when the design?
I'm not sure I understood the whole question. So how do you know when? I'm sorry?
So when suppose the team of the design engineers are designing the project and the contractor did not let them know everything about the project.
Well,
so how do you deal with that?
that's a little bit rare because
Then you come back to the.
So the question was, I think in essence, paraphrasing, what happens when the contractor is not forthright with all the elements of the contract and the design? I haven't seen that before, and here's why. The contractor's at serious risk. A $200 million job these days is relatively small. Your mid-sized jobs getting $500 million. You see billion-dollar jobs all the time. Several are fictional-led in Texas. And there is so much at risk that I don't know that it serves a contractor's benefit to withhold information from the design team. Things are very well documented as well. All the information is sent by transmittal. And so to the extent that a contractor ever wasn't forthright, it would be very well documented that, hey, look, our design basis is that, and now all of a sudden you show up with a new design criteria, right? Now, there are instances when the contractor and the engineer are working together and they develop a roadway profile line and they start to realize, look, man, we're going to have a better, more competitive design if we split the PGL and we run dual PGLs with a medium, okay? But those are collaborative things that happen. It does change the design. The key there is to emphasize, look, that's a great idea. We're going to go ahead and split or bifurcate the PGLs for this roadway, but all of the design that we've done for the sound barrier walls, the traffic barrier rails, the drainage, we've got to revisit in light of the new PGL, right? All of the other interdisciplinary designs have got to be involved in that decision, right? But I think they're going to be generally pretty forthright, because otherwise it's just going to cost them money and time. Yes, sir, Anwar.
Just a segue to that same question. In the design field work, you start with the conceptual design bid on. And the design is ever evolving even during construction.
Yep.
Right? So how do you manage that in the contractual work, for example, the geotechnical consultant come along? What kind of blend do you propose to the contract
You've got the hammer in your hand and all the problems are nails, right? So that's a very good question, and that is a very practical question. How do you handle scope creep? Okay, you don't even have a 30% design. Okay, so first of all, you have an engineering firm that's done a few design builds, and they pretty much know how it's going to evolve. You have a contracting firm that's done a few design builds, and they pretty much know how it's going to evolve. Proactive interaction in the risk registry, because right before the bid, everybody should have a pretty good idea of what kind of job everyone's done. You know, the design engineer is going to say, look, we had enough time to deal with the profiles, reasonably confident with drainage, but we really didn't get down to the sound walls and where the CTBs go, right? We don't know if we can put scuppers in. We don't know if we can go with the wire guardrails as opposed to the CTBs, the concrete traffic. You know, issues are going to come up through design. The engineers are going to be focused on the backbone of the design, but they're going to be cognizant of those issues that are still out there yet to be refined, and have very candid input on the risk registry. Look, we're not quite done with the CTBs. We're reasonably confident, we're like 50% confident that we're good with our quantities right now. What's the exposure? Assign a dollar value to the exposure. And that's really what's done as a practical matter in the industry on successful joint ventures. You have that relationship of trust, that daily interaction that's going on all the time, and you have an elaborate risk register that articulates everything that the contractor and the engineer can envision, and it assigns a percentage of probability or possibility, and it assigns a dollar value. And you're driven to your contingency, and you include that in your bid. Now, what you'll find as a practical matter when you get there, when you get to your IFC, RFC drawings, is that yes, you're going to go over in quantity with certain items, you're going to go under with other items. And a good team, it's almost going to be a wash. You're going to know the big issues. You're going to know if it's a balanced job or not a balanced job. You know, you're going to know the big things. I would watch drainage and rails in highways, you know, but the bigger issues are going to be resolved, or pretty close to it. The detailed design won't be, but the bulk of it will be pretty well figured out.
So, for a engineer, the fee is 0.5% or 0.6% of the build cost. The contractor has more skin in the game. In your experience, have you seen that the engineer has enough say in the design? No, this is my design. We need to do it this way. Talk to the contractor. You can't force me to do something you just want.
On the best design build jobs, there's friendly debate that's advanced by another engineer that's on the contractor side of the fence, qualified. At the end of the day, the engineers have that responsibility. They have the professional liability policies. They have the standard of care. And I've not seen an occasion where the contractor tried to strong arm the engineer into doing something that the engineer did not feel was adequate or sufficient. If you get to that place, then you're in a very problematic design build. I mean, that is not going to be a successful design build for any abundance of reasons that may very well transcend the engineering effort.
All right.
Thank you.
Can you stand here for a minute?
yeah.
I've got something for you. Thank you very much, Mark, for this eye-opening lecture about the intricacies between the business side and the engineering side of our profession. I'm sure that your grandfather would be very proud of you. I have a plaque for you. Before I give you the plaque, I want to let everybody know that along with the plaque comes an honorarium. And Mark has decided to donate the honorarium back to the Buchanan Chair, so we very much appreciate that, sir. So the plaque reads, Texas A&M University, Zachry Department of Civil and Environmental Engineering recognizes Mark W. Buchanan for presenting the 30th Buchanan Lecture entitled Risk Mitigation in the Changing Relationship Between Contractors and Engineers. And it's signed by Professor Graisley and myself. Thank you so much. Thank you so much. Go ahead. I'll give you that. Thank you. Well, that concludes our 30th Buchanan Lecture.